Okay, guys, so we looked at a real life example of kind of what we're doing, and now we're going to turn it over and we're going to go back to this definition that I'm currently showing you. So I do want to remind you, we say that the limit as x approaches a of f of x equals L. This is not new to us, but we're going to actually really focus on this second part to this definition. So if for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x, or absolute value of x minus a, less than delta, then f of x minus L, the absolute value of that is less than epsilon. So what we're actually going to be doing in this next example, these next two examples, is we're going to be applying this to this second part of this rule here for the every epsilon greater than 0. So a couple of things that we want to make sure that we are paying attention to here. Please notice the x minus a comes from whatever variable that you are plugging in for f of whatever. So in this case, that's why they use x. That's why they got x minus a. The a comes from, the a comes from here, this a that you're approaching, right? So that's how they're going to get that statement. The L is going to fall into that f of x. So whatever your function is what's going here, so on and so forth. So we're going to put this to use. The thing about this definition, guys, is it's really the delta and the epsilon that we have to come up with. So we're just going to practice like splitting this thing apart first, and then we'll talk a little bit more about how to come up with the epsilon and the delta, probably in the next video. All right, let me clear this out and we're going to do an example. And it never fails. I have a cold. That's what happens every time I do one of these stupid videos. So let's look at number 177. So in the following exercises, write the appropriate epsilon minus delta definition for each of the given statements. So they want me to write out that expanded piece of this. So in number 177, they give me the limit as t approaches b of g of t equals m. So if you're having a hard time visualizing this, what I might recommend is that you go back, pause the video, go back to that definition, write it down so that you can look at it as we go through this. Okay, so here's what happens. I'm going to set this statement up. I'm actually going to flip my computer here to make it easier for me to write this. So I'm going to set this statement up to say, so we start off with for every epsilon greater than 0, and this is the way they always start out, there exists a delta greater than 0, okay, such that if 0 is less than, now this is where we actually need to include what's going to be in here. So the 0 and the delta are standard to this statement, but we need to actually pull this information out. It's going to go in this absolute value from the information given. So remember, that was actually the variable that you were using minus what you're approaching. So the variable that we are using in 177 is t, right? Because it's t approaches b, so this is going to be t minus b, because that's what we're approaching, is less than delta. Then absolute value of, now this is going to be our function, right? So it's f of x minus L. In our case, we don't have an f of x, we've got a g of t. So g of t minus, what was the limit for this one? So the limit for this one was going to be m. And then that needs to be less than epsilon. All right, cool. So again, the only things that we changed was this part here and this part here. That's how the definition works. Now you are going to see as we move through these next examples, not so much this video, but the next video, we're going to have to figure out what delta and epsilon have to be. All right, cool. Let's do one more just to make sure that we're good with that. So I'm going to clear this one out. We're going to do number 179. I really shouldn't have cleared all of that out because most of it's going to stay the same. So I'm actually going to make it easy on myself, and I'm going to say, okay, so for every epsilon greater than 0, there exists a delta such that this part needs to change and this part needs to change. Let's do it in a different color so we can see it really well. Okay, so on 179, we have the limit as x approaches a. That particular variable there, that Greek letter, is a phi. That is a lowercase phi. Don't feel bad. I had to look it up. It's been a long time since I've looked at my Greek letters. So we've got a lowercase phi here of x equals a. All right, so the 0 less than the absolute value of delta, that's where we're going to talk about what variable it is we're looking at and what we are approaching. So on number 179, we are going to have x, because that's the variable I'm using. Are you going to let me write? X minus, now what are we approaching here? Lowercase a. And of course, this should be understood at this point, guys. There is a huge difference between lowercase letters in math and uppercase letters in math. It's not like English. All right, so delta, then the absolute value, this is where we use our function minus our limit. So our function in this case is phi, which we make a terrible phi. That's not too bad. So phi of x minus, and of course my limit on this one is a. So there's your standard definition. So all you have to do is take what you're given and kind of situate it, what variables are using, what are you approaching, what's your limit, so on and so forth. All right, so now we're going to do some graphical examples of this. Guys, I really do think the graphical examples of this help. It kind of makes it make sense what we're doing. I'm going to clear this out. We are going to go to number 181. So the following graph of the function f satisfies the limit as x approaches 2 of f of x equals 2. In the following exercises, determine a value of delta greater than 0 that satisfies each statement. So our statement on number 181, I really want to be able to show this. At the same time, let me show it at the same time. Okay, so if 0 is less than the absolute value of x minus 2 is less than delta, then f of x minus 2 is less than 0.5. So they're giving us these statements. We know how to build these statements. So we know that x is approaching what value? Well, that would be the 2, right? X is approaching 2. We know the limit that as x approaches 2 is going to be this f of x minus 2. And then this 0.5. Now this is different than what we had, because in our definition at this point we had less than epsilon. So what I know from that now is that this value here is epsilon. So that's my epsilon. So basically what happens is I know I'm dealing with the point as x approaches 2, and we know the limit's 2. So I know I'm dealing with this point right here. This is my point. Now, these graphs kind of are off a little bit. This point's actually 2, 2. On my end, which it may not be that case on your end, but on my end, it looks a little off. But that point's actually 2, 2. So what I want to do is I want to go 0.5 on either side of 2. And this is in terms of the x values. So I'm going to take my, or excuse me, no, this is in terms of the y values. I am so sorry. This is in terms of the y values. So I know I've got 2 here, and I want to go 0.5 in either direction from the 2 on the y-axis. So if I go 0.5 up, that's going to put me right here, right? That's going to put me at 2.5. And if I go 0.5 down, that's going to put me at 1.5. Sorry, I was trying to read my notes. I've scribbled something here that I was wanting to say. So what I want to do now is I want to figure out, okay, so if that's the x values, right? That's kind of what I'm looking at and change. I keep saying x values, y values. That's the y values. So that's my change in the y values. I now want to figure out what x values correspond to those y values. So if I go through and I figure out, so it looks like 1.5 is going to be right about And again, this graph is a little bit off here. It's actually supposed to be right there. So that looks to be about 1.75. Man, I've made a mess of this, haven't I? So this is 1.75. That's going to be the value that corresponds to your 1.5. Now I'm going to do the same thing for 2.5. So for 2.5, I'm going to come over here, and it looks like with 2.5, looks like I'm right at about 2.5 as well. So okay, so now what I want to do is I want to figure out what's the difference between these two and 2. So what I'm trying to do here is I'm trying to figure out what delta is going to be associated with this epsilon of 0.5. So to do that, I'm now going to focus on my x values. I'm going to focus on what's going on here. So it looks like for this one, I have, so let's see. So we have a difference of x's. All right, so let's do some math here. So one of my x's is going to be 2 minus 1.75, right? That was the one to the left of 2. And if we do that, we get 0.25. And then I also had the 2.5 minus 2. So I'm just trying to figure out what's the difference between these two values that these epsilons created. So 2.5 is equal to 0.5. And remember from the first video I did from this section, we said, oh, when you're finding, and in that particular video, this was in terms of tolerance, right? So we talked about when you're doing this, you always want to go with the smaller value. So in our case, our smaller value is actually this 0.25. So it actually turns out delta in that case has to be less than 0.25. So remember, the epsilon in this case was associated with the y values. The delta is going to be associated with those x values. How do we get to that delta? So we went through, we figured out what, if I moved up 0.5 above my y value and 0.5 below my y value, what x values were associated with that, and how did that difference affect the two? Cool. I think we should do this process again. So I'm going to clear this out. Let's do another one. So I want to do, let's do 183. So again, the following graph of the function f satisfies that x approaches 3 of f of x equals -1. In the following exercises, determine a value of delta greater than 0 that satisfies each statement. All right. So here's what we're looking at. Again, I know I'm approaching 3 because that's the value that ended up there. And I know that my limit's going to be 1. So we are looking at the point that I'm going to be focusing on is going to be 1,3. Or excuse me, 3,1. I can't do, my math is all backwards today. 3,1. Okay. So again, this value here is my epsilon. So we're going to do the very same process that we did in the last one. 3, -1. I said +1. 3, -1. Because we want to figure out what we're approaching as we approach 3, right? There's our 3, and then of course we are approaching -1. Okay. So we want to focus on what's happening around -1. And since my epsilon's 2, I want to go up 2 from -1, and I want to go down 2 from -1. So if I go up 2 from -1, that's going to put me right here. So one of my values I'm going to be dealing with is 2. So this one's actually a little nicer than the one we did before because I'm not having to deal with those half values. And then if I go down 2 from -1, that's going to put me at -3. So I want to figure out, no, let's count. Let's count, shall we? If I go up 2 from -1, 1, 2, that's going to put me at 1. There we go. So we've got 1. And of course, the -3 was correct. I hate being sick in the summer. Okay. So now let's figure out what x values are associated with these y values. So I do think we have an x value here. Let's do some different color of 1, right? That's where we're going to be crossing there. So one of my x values is going to be 1. And then with -3 here, it looks like I'm going to hit -3 when I am, I believe, oops. Let's see. There we go. When I am 5. So the x values that I'm going to be associated with now is going to be 1 and 5. So let's make our statement here. So we've got and everything's kind of focused around this 3, right? So I'm going to do 3 minus 1 equals 2. I'm going to do 5 minus 3. So everything's kind of associated around this 3. I want to figure out the differences too. So with this particular one, I don't have to worry about picking and choosing. It actually ended up being the same value. So therefore, and of course in math, the way we write therefore is this triangle with the 3 dots. Therefore, your delta needs to be less than or equal to 2. Cool. Just trying to think here. So that's, I feel like I butchered this problem. But guys, of course, if you have any questions, you can always email me. We can go back over it. By the time you email me, I won't be sick because this will be 2 weeks out. Okay. Trying to think here. Is there anything else I want to do? Let's do this one. This one's kind of, maybe we won't do this one. I'll just talk about it. Trying to think here. It doesn't do anything. This one's not anything different. It's just they don't put it in terms of this. They just say, oh, let epsilon be equal to 3. So they're telling you what you need to be equal to. And here you want to find the limit as x approaches 3. They say is 2. So you're focusing around the 0.3 comma 2. Yeah, that's the same thing we've been doing. All right, cool. So I'm going to stop this video here because this is kind of here's examples where you can actually see this put to use. In the next example that I'm going to do, we are actually going to figure out what epsilon and delta have to be. So I'm going to work backwards from what I just did here. So I'll see you in the next video.